Hello students, welcome back to the channel. In the last video we have seen the last application of dimensional analysis. In fact the last two applications of dimensional analysis. One was derivation or deduction of relation between physical quantities, and the other was conversion of units. Okay. Now in this particular video we will be starting with the measurement part. Okay, so as the name of the unit is units and measurement, so we will be starting with the measurement part of the chapter. Let me put the heading. So there are two important terms that we need to understand related to measurement. First one is accuracy. So there are two terms, one is accuracy and the other one is precision, and many often than not student do feel difficulty in differentiating between these two terms. So let us talk about accuracy first. Okay. Accuracy gives an idea, it gives an idea about how close the measured value is to the true value. So that means the closer the measured value to the true value, higher will be the accuracy. Okay. And the next term is precision. Okay, so the precision tells us that to what degree or what resolution or to what limit the physical quantity has been measured. Okay, to truly understand what exactly precision is, we have to take an example, but let me first write the definition here. Okay, so precision tells us to what resolution or limit the physical quantity has been measured. Okay, so the precision of any measurement depends on the least count of the measuring instrument. Okay, precision depends on the least count of the measuring instrument. Okay, let us understand this with an example. Suppose we have an object whose length is exactly 5 centimeter. Okay, suppose the true value of this true length of this object is known to me, and that is sorry. Okay, now if I give this object to some 5 students in the class, and if I ask them to tell me what is the length of this particular object, and suppose the readings that I get from different students are 4.5 centimeter, 4.90 centimeter, 4.99 centimeter, 5.2356 centimeter, and 5.3 centimeter, or 3 to 1 centimeter also we can write. Okay, now if we need to figure out which is the most accurate measurement among these values, then our answer will be the third measurement, which is 4.99 centimeter. Okay. This particular measurement is the most accurate measurement. Why it is the most accurate measurement? We can see that this value is closest to the true value. Okay, so if I compare it with the other measured values, 4.99 is closest to 5 centimeter. So that makes it the most accurate measurement. Now if you talk about the most precise measurement, so here the most precise measurement will be 5.2356 centimeter. Okay. Now I hope you are getting some idea why this is the most precise measurement. Okay. So the idea here is, here you can see that the measurement has been done till 4 decimal places. Okay. Now whenever we are taking any measurement, we cannot simply put these decimals. It depends on the least count of the measuring instrument. Whenever we write any scientific measurement, we have to write it in such a way that it should give an idea about the least count of the measuring instrument. For example, if we take our normal centimeter scale, I happen to have a picture here. The least count of centimeter scale is 1 mm, right? Now suppose if I try to measure length of any object, something like this, and if I start from 0, where exactly it is coming, let me check. Okay, so you can see that if you are taking a measurement from this centimeter scale, someone can write this measurement as 3.2 centimeter, or someone can write it as 3.3 centimeter. Okay, but we should not write this as 3.25 centimeter. If I'm writing it as 3.25 centimeter, then that is very wrong. Why? Because the least count of this centimeter scale is 1 mm. So we can put only one digit after the decimal. If I'm writing 3.25, then this 5 is just a guessing. This value we are not getting from this centimeter scale. We can get only up to one decimal place from this centimeter scale. If we had used a vernier caliper, in vernier caliper what happens is that this gap between 3.2 and 3.3 is further divided into 10 parts. Okay, so if it is further divided into 10 parts, then we can get one more digit after decimal. Okay, in that case, suppose if this is a 3.2 and this is 3.3, let me bring it down a bit. And this is further divided in 10 parts, for example. And if the object comes somewhere here, suppose somewhere here, so in that case we can write it as 3.23 centimeter, or because this is suppose 1 2 3 4 5, then it is between 3 and 4, then someone can write it as 3.23 centimeter or 3.24 centimeter. Okay, again we should not write it as 3.235 centimeter, because sometimes we do, because again this 5 will be just a guess letter or guess digit, you can say. Fine. So I hope you are understanding. Here the least count of vernier caliper, if I take, that is 0.1 mm or 0.01 centimeter. In that case we can write two digits after the decimal. But in case of our normal centimeter scale, we can write, and in fact we must write only one digit after decimal, because if you try to increase the number of digits after the decimal, that is going to give a wrong impression about the least count of the measuring instrument. Okay, so the student who gave me the reading as 5.2356 as reading, he must have had a very sophisticated instrument, some electron microscope or something like that, where he can take very small measurements. But for some reason he was not good at taking the measurement. He did not take the measurement properly. Because of that, his reading is not accurate, meaning it is not the most accurate one, but it is the most precise one. Okay, now it is not always necessary that the most accurate measurement and the most precise measurement has to be different. They can be same also, you know. If the person who is taking the measurement, if he is having the right kind of instrument, and if he or she is following the right set of instructions, if he knows how to take the measurement properly, then he can also give the most accurate measurement. Fine. So the main difference between accuracy and precision is, accuracy gives us an idea that how close the measured value is to the true value, and precision gives us an idea that till what degree or resolution or limit till which the measurement has been done. And the important point is that it depends on the least count of measuring instrument and the number of digits that are there after decimal in the measured value. Okay, so here I hope you know what is least count of a measuring instrument. just in case if you don't, I'm just going to write the definition here. Okay, so least count of any measuring instrument is the minimum value that can be measured from the instrument. So it's a very simple definition. So least count is the minimum value that can be measured from the instrument. Fine. Now let us move to the error part a little. Okay. Here also we have a bit of theory, but we need to go through it anyway. So the next term is error. So error occurs when the measured value is not same as the true value. And mathematically, if you talk about the error value, so we are going to define error value here. Error value is the difference. It is the difference between the measured value and true value. Okay, so whenever we are calculating error value, it is simply the difference between the measured value and true value. Okay. Now we have two types of error. So let us quickly understand what are the types of error. So error has been divided into two categories. One is systematic error, and the other is random error. Now let us understand the difference between systematic error and random error. Systematic error occurs in one direction only. Okay. Systematic error occurs in one direction only. What does this mean, that one direction only? What it means is systematic error is either always positive error or always negative error. Okay. Positive error is when the measured value is more than the true value, and negative error is when the measured value is less than the true value. Okay. So systematic error occurs in one direction only, that is either always positive or always negative. Okay. Whereas random error can occur in any direction. It can be either positive or negative. Okay, so random error does not have a fixed direction. Okay. Now, if we talk about some reasons or the causes of systematic error and random error, then let us see one reason for both. For systematic error, the reason is improper design. One of the reason is improper design or calibration of measuring instrument. So the cause is improper design or calibration of measuring instrument. Okay. What it means is that whenever we are trying to take any measurement from any measuring instrument, there is a high probability that that measuring instrument may have a zero error. Okay. There is a high probability that that measuring instrument may have zero error. What is the meaning of zero error? Zero error is the measurement that we get from any measuring instrument when the measurement is supposed to be zero. Meaning, if you have not taken any measurement, for example, if you take an ammeter in 10th standard, you all might have conducted Ohm's law experiment, in which we get a big box shaped ammeter in which we have the readings like 0, 1, 2, 3, 4, something like that. Similarly on the left side as well. Now what happens is that if we have not connected this ammeter to any circuit, in that case the reading of the ammeter should be 0. Okay. But sometimes what happens is that even before connecting the ammeter to something, it will be showing some reading. Okay. It might show some 1 ampere or something like that. So in this case what happens, whatever measurement you are going to make from this particular instrument, you will always get 1 ammeter extra reading. Meaning, if the true value of the current is 3 ampere, the ammeter is going to show it as 4 ampere. Okay. To get the true value, what we need to do is we need to calibrate this measuring instrument. Calibration means making the measuring instrument zero error free. Okay, so if you do not calibrate this particular instrument and keep using the same instrument for taking different measurements, what is going to happen is that we are always going to get a positive error. We'll always get 1 ampere extra current value. Okay, now the good thing about systematic error is that it is always in one direction, meaning later even if you realize that there is a zero error of 1 ampere, you can go back and correct your readings, yes or no, because you will be knowing that whatever measurement you have taken will be having an error of 1 ampere, so you can simply subtract 1 ampere from all the measured values and you are going to get the true value. Okay, so that is how systematic error works. Here the error is always in one direction, and even later after the measurement we realize that we have made some error, there is a high chance that we will be able to rectify it. Whereas random error, there is no such scenario for random error, because here the error can be either positive or negative, and the reason, the cause for random error is improper measurement environment. Okay, so if there is any sudden fluctuation in the measurement environment, like suppose if there is some fluctuation in experimental conditions like change in pressure, temperature, humidity, these things can lead to random error. Okay, or you can write the cause as fluctuations in experimental conditions. Okay, so for example, if you are doing any current electricity related experiment and suddenly if there is a voltage spike, or if there is some voltage fluctuation, if the voltage goes down, in that case your readings can vary and you cannot predict what is going to happen to the voltage. It may increase or decrease, so that kind of situation leads to a random error. Okay, or if you are conducting some thermodynamic related experiment and if there is a sudden change in the temperature or pressure of the surrounding, or if wind starts blowing, then those things can lead to random error. Okay, and so I hope you have got some idea about the difference between the random error and systematic error. So now we will move to few important terms related to measurement values. Okay, okay, so now let us see some terms related to measurement values. Okay, So whenever we are conducting any scientific experiment, okay, we do not take the measurement just once. Okay, so there is a certain procedure, there are certain values we calculate before finally representing our data. Okay, so for example, suppose if you are assigned a task to measure the time taken by an object to reach the ground when it is dropped from a tower of certain height h. Okay, now suppose if I am assigned this task, that someone tells me that find how much time an object will take if dropped from the top of the tower to reach the ground. Then to conduct this experiment, what I can do, or what I will do, is I can take help of my friend. I can ask him to go to the top of the building, and I'll be standing near the foot of the tower with a stopwatch, and I'm going to ask him to drop the object. So I'll start the stopwatch when he drops the object, and I will stop the stopwatch when the ball just hits the ground. Okay, now I'm pretty sure you all can understand that I cannot get the exact time in just one experiment, or in just one go. Okay, because there are many ways in which error can happen. It may happen that the person has dropped the object, but I started the stopwatch 1 2 seconds late, because human error is always a possibility. And there's another chance that the ball might have already hit the ground and I stopped the stopwatch 1 2 seconds late, or in a hurry I might have stopped the stopwatch 1 2 seconds before the ball hits the ground. So you can understand that there are various ways in which error can happen, and same goes for any experiment, any kind of scientific experiment. Whenever it is conducted, we can never be 100% sure that we are going to get the exact value in just one attempt. Okay, so here what we do is we have to measure the times certain number of times, meaning if I talk about this tower example, then I have to ask my friend to drop the object a couple of times, and then there are certain calculations I will perform before finally representing the result of the experiment. Okay, so let us understand what are the values that we calculate. So the first term is mean value. Okay, the first term is mean value. Mean value is the average of all the measured values. Okay, so as I told you, in any experiment we don't conduct the experiment just once, we conduct the experiment many number of times. Okay, so for example, let me put this down. Suppose the measured values are some a1, a2, a3, so on an. Okay, so once we have the measured values, the first thing that we calculate is mean value. Mean value is average of it is the average of measured values. Okay, so mathematically if I write this mean value, a mean will be the sum of all the measurements, that is a1 plus a2 plus a3 so on till the nth measurement an divided by n. Okay, and we can represent this in terms of sigma as sigma ai, I equal to 1 to I equal to n whole divided by n. Okay, so after calculating the mean value, so like in the case of the time experiment that we are conducting, after I take some certain number of measurements, first I'll be calculating the mean value of time. Okay, after that we calculate absolute error in each measurement. Okay, absolute error is mod of the error values. Absolute error is the mod of the error value. Okay, so for example, mod means absolute value. Like if you have plus 5, its mod value is 5, and if you have minus 5, then its mod value is also 5 only. So here we focus on the absolute value of the measurement or the quantity. We ignore the positive or negative sign here. Okay. So mod delta a1 is the absolute error in the first measurement. That will be mod of a1 minus a mean. Okay. Then we have mod of delta a2, that will be mod of a2 minus a mean. Okay. So on, we have mod of delta an, that is mod of an minus a mean. Okay, so here we are calculating the absolute error values in all the measurement. Okay, so first we calculated the mean value, then the absolute error value, and then we calculate mean absolute error. Mean absolute error is average of all the absolute errors. Okay. Mean absolute error is simply average of the absolute errors. Fine. Mathematically we can write delta a mean as mod of delta A1 plus mod of delta A2 plus mod of delta A3, or I can simply write so on mod of delta AN by n. So this becomes the mean absolute error value. Okay. Now we are close to our final representation. So once we have calculated all these values, that is the mean value, absolute error, that is the mod of the error values, and mean absolute error, we go for the final representation. Final representation of the measurement. Okay, so finally the measured value is represented as, suppose we are measuring the quantity A, that will be written as A mean plus or minus delta A mean. Okay. So from this representation, what the person who is studying or reading this data needs to understand, or what this representation is trying to tell, is that I cannot tell you the exact value of A, but A value will lie between A mean minus delta A mean. Let me create some space here. So it will be greater than or equal to A mean minus delta A mean, and less than or equal to A mean plus or minus delta A mean. Okay. Now what this means is, for example, the experiment that we were conducting, if the mean value of time came out as 10 second, okay, suppose the mean value came out as 10 second, and the mean absolute error came out as 0.2 second. Okay, then finally how I am going to represent my findings or reading is, I'll say that time is equal to 10 plus or minus 0.2 second. Okay, so from this, what the person who is going to read this data needs to understand, that the time value can lie anywhere between 10 minus 0.2 second to 10 plus 0.2 second. Okay, meaning the time taken by that object to hit the ground will be somewhere between 9.8 second to 10.2 seconds. So I cannot tell him the exact value of time, but this is the range in which the time will be lying. So accordingly he needs to utilize the data. For example, if he is trying to design a parachute and he is trying to figure out whether the time will be sufficient for the parachute to get inflated while the person is in the air or not, he can decide based on this value. Yes or no? Meaning the time taken by the parachute to inflate should be less than 9.8 seconds. Then only it will be helpful for the person, or even lesser than that. Okay, so that is just a hypothetical example. Now two last terms we will see, and then we are going to wind up this session. So another term we have is relative error. Okay, relative error, it is simply the ratio of the mean absolute error and the mean value. Okay, so what is relative error? Relative error is equal to delta A mean by A mean. Okay, so basically the mean absolute error by the mean value, or if the true value and the error values are known, then it is the ratio of error value and true value. Fine. And the last term for today is percentage error. Percentage error is relative error into 100. Okay, percentage error is relative error into 100. Okay, so mathematically I can write this thing as delta A mean by A mean into 100, or error value by true value into 100. Okay, so these are important terms. Sometimes we are asked to find these values directly. Okay, so I hope this session was useful. In next session, in the next video, we will be studying about combination of errors, and we'll also discuss few problems based on that. Okay. Okay students, thank you for watching, and if you do like the video, please hit the subscribe button. Bye bye.